Wow.
Okay, you're on.
We think.
That's why his kid couldn't come.
Well, it's a good thing Lloyd's out here, our treasurer, secretary. So we do have a treasurer here. So. And it looks like he's looking at his books right now. So how much money do we have in the account?
$10.
$10. So in the past, I've had recruiters come in to bring pizza. Yes, C++ is growing in this community. I can tell by the number of people here. It's a good sign. But things have sort of dried up, but we will try again to get more people to come here and get us some food so we can have a longer time to discuss things. Fortunately, my presentation is quite short. As I said, I've been preoccupied with other activities, and but I really wanted to get into this issue because we're trying to reach more of the inexperienced crowd, but I see that we have a lot of experienced people here today, so maybe we could just have a lively discussion about what we need to do. So my name is Brett Searles, and the purpose of this is a multi-part series of lectures. It's to just help look at certain functionalities, certain ways we write code, and how they may affect performance or affect memory usage. So they may be correct, they may work well, you may not get any compiler errors, you may get your code to work correctly, but if you really look under the hood, you're nearly not doing the best way of looking at the complete system that you're working with. So like I said, it may be valid, yet destroys the performance of your application. So we're going to give some references so that we can build upon topics presented tonight for future lectures. And we'll give some food for thought. So when you're writing your application, you can say, maybe I got to look under the hood and see what I'm really trying to do. So everybody here probably knows assembler. I love assembler. Actually, I love assembler more than I love C++. And I love machine code probably even more, but I'm not going to get into that. But what are they? They're locations in the memory that are directly accessible by instructions. So they're like right next to the instruction, and they are used by the processor to do the work. And it's sort of like a scratch sheet of paper. And we have registers of different widths, from 8-bit up to 36-bit. I'm working with PDP-10 now, so I got to include them. So.
XKF.
Yes.
You're the one.
So.
Excuse me, you mean PDP-10 use 36-bit registers?
Yes.
Okay, what's the main purpose?
That's just the way they decided to do it, and I think
It was very reasonable for the time frame.
I
Well, it's
mean,
36-bit words or something,
It was
right?
a
Right.
36-bit word and had a lot of reasonableness.
Yeah.
A great architecture level.
What's
The PDP-11
What's the
better.
date for that architecture?
that was back in the 1970s.
Okay.
60s.
60s.
Like
It
Before
was
the
used for
model-based
mainframes, built by DEC. However, because of the influence of Intel and ARM, basically now it's 8-bit word or 8-bit bytes and 16-bit words. So, like I have here, that we have the Intel registers, like the AX, which is usually called the accumulator, and it can be broken up into 8-bit words for AL, for low and high, and then 32-bit registers as well as 64-bit registers. And in ARM, they also, and with the 64-bit processors, you have an extra 8 registers to work with, and you also have the FPU, the MMX, and also the SIMD registers or the SSE registers. ARM, as you know, has 16 registers from R0 to R15, and the R13 is for the stack, so that's where you basically watch when you're working with the stack memory. R14 is basically the IP of the address that did the call, and RC is for the program counter. And they repeat the registers for the supervisor. They also have registers for our Neon, which is their SIMD version. So how do we access the memory? Well, we have 2 locations, the stack and the heap. And in the stack, we have a place to hold memory for quick access. And the memory usage is temporary, except for the interrupts, which are usually at the beginning of the memory locations in the RAM. And when the process starts, the OS assigns a block of the stack to be used by the application. And it can be divided up into local storage for the threads and fibers that run within an application. And this is all done by the OS. So let's look at the heap memory. Again, it's a location to store allocated objects or variables. So the memory is not temporary. So we need to deallocate the memory in order to free up space in the heap. And we have the base address that can be stored in the stack as well. That's the base address of the object, like a strut or a class. So now going back to the stack, what happens with the stack when we call a function in C++? Well, first we push the parameters that are passed to the function, like here, parameters 1, 2, and 3. Then we push the IP of the address from the place that called the function, and so that when upon return, it will go back to the correct location. And that would be right here in the return address. And we can subtract from the stack any local variables. So if we have local variables, we would subtract how many variables, like plus or minus 12 for this example. And we also have an option for the base pointer to point to where the frame pointer was set, or we can do what we call frame pointer optimization, which we don't use. We would free up the use of the base pointer to be used with other operations. So let's just do a little bit about instructions. So we have 2 ways of reaching an instruction. One is through jump, and the second is through call and return. And they can be any one of the following types. One is a near, which is a jump to an instruction with the inside the current code segment. Short is within 255 bits or bytes of where your current location is. A far is a jump to another application, but that has the same code segment security. And then we have task switch, which is a jump to another task, like a jump to an interrupt service routine. So now let's talk a little bit about optimizing your code. So if you look at this function, what is wrong with it?
Other than inconsistent curlies?
Well, the problem with it is that we are going to be affecting performance by putting this try-catch point. So let's look at it from the perspective of C. So first of all, in C, you would first of all have a variable called and which is pointing to a jump buffer, which is an array type, which has information that is used to restore back to the calling environment. So when you do a try and it comes back, it fails, you want to save that environment so that when you do your long jump, like this, you know where to return back to. Now what is happening in the long jump? Well, it's actually a task switch. So now we have to look at the different descriptor privilege level. Like in Intel, they had 4 levels, but most other chips it has supervisor versus user mode. So we have to do a major, store all your IP flags and registers so that we can do this long jump. And so this will cause a huge performance hit. So what can be done? Well, in the C++, especially in the gaming industry, they like to use this concept called no except. And this will force the code to not throw any exceptions when it is executed. However, if an exception does occur, it's going to blow up.
Sorry, is that internal exceptions or only exceptions that exit the function?
That's
If you
internal.
have a try-catch,
Yeah, but
inside
that was
the
only
function.
to that particular function. So that function will not throw any exceptions.
okay, it won't throw out.
Right.
Got it, thanks.
So what is the best solution? And that is, we should check your variables for any issues that create undefined behavior, because if we can do that, it won't throw any exceptions, and therefore our code will be better performing. So my conclusion, and that was only 12 minutes, good. Even though there may be coding practices that are correct, there may be other issues that are happening under the hood that affect performance. And in today's environment with mobile and IoT, it's very important to consider these because you have to consider power consumption, memory usage, and other things like that. So, any questions, any comments, any discussion, I'd love to hear your thoughts.
For me, it is curious to know more details about internal mechanisms of the exceptions in general. For example, many articles state that nowadays the compilers so smart that they generate code having nearly zero cost abstraction if exceptions don't happen. Whereas Walter some time ago said that zero cost exceptions are a myth.
They're a fraud, yeah.
So I would like to know what exactly happened, what kind of code the compiler generates to work with the exceptions in case the exceptions never happen, don't happen, and what is actual cost of that? How close it is to the zero cost exceptions?
What is the code that is generated that gets executed even if you don't have an exception?
Yes.
That's what he's
Yes.
right?
Well, I mean, you won't have the extra variables that you have to push and pop from the stack. And
So, no, it's
so that extra variable, that jump buffer, is automatically added to the code from the try catch.
Okay, so that actually is invisible because you're making space on the stack anyway. It's what's the code that gets executed that would fill that buffer? How bad is it? How much code, you enter a subroutine that's got a try catch in it.
Mhm.
What are the instructions that will get executed that store whatever crazy pieces of information that will be used in case there's an exception?
And you haven't written a try catch.
You've written a try catch.
Well, the information would be the the array that would be holding the information about the caller, and when it does the jump to the interrupt service routine, then it will know where to come back to.
Understood, that's what happened, but if you don't have an exception, it's how many instructions and what type of things are stored.
Oh, well, it would become 0, and therefore would just keep going to you would continue executing the code if you have no exceptions.
Yeah, that's the idea. What's the cost of allowing exceptions if you don't actually throw an exception?
The cost would be pushing of the environmental variable and popping of it. So it's 2 operations.
Well,
Go ahead.
if you disassemble the output of the compiler for even with simple try-catch, you'll be horrified. For one thing, the try-catch pretty much disables the optimizer. You're not going to get registers or variables assigned to registers because when the compiler tries to remotely transfer execution into a catch block, it can only access variables on the stack. If you have variables in a register, it doesn't work. So, the registering of variables that are live in a catch block is broken. Second thing is there's just too many possible transfers of control around when you have a catch tries and catches, and it just kind of defeats most of the flow analysis optimizations, and the compiler just gives up on that stuff. Second thing is you have to build a stack frame that can be unwound, which is not necessary if no exceptions can happen. So it's not 0 cost, it's not cheap, it's not free, and if you really want your code to be fast, you just make it no throw code.
Or don't accept yet.
Or no except C++ equivalent to that.
Then what does make the article writers to assume that currently the exceptions are so cheap? Why do they write that?
You'll have to ask them. Just take any compiler and just, clean up the code, do a malloc and then free the code and do a little bit in there, okay? And then do it with RIAA and call a couple of functions in there and compile it with your favorite compiler, disassemble it, and look at the difference.
So one really useful tool to check out this sort of thing is the compiler explorer, where if you just look up on Google, look up compiler space explorer, and put in some sample code with a try block versus not a try block, and see what the assembly language output is.
Godbolt is a good version of the compiler explorer.
Yeah, that's what I'm talking about, the Godbolt one. That's really good to check out this sort of thing, and then you can see what's really being done and what's not.
Really, you can't learn to write fast code without looking at the disassembled output.
Right.
It doesn't really matter what the textbook says. You have to try writing your code various ways and compile it and disassemble it and look at it and see if that's what you want. That's the best way to do it if you want to write really fast code.
I have a question. I understand what you're describing about the compiler's flow analysis, etc. The question that I have is if the try block is a substantial amount of code, let's suppose it's, a couple hundred lines worth of something, somewhere in the middle of which something might go by. But Is the compiler but in terms of nominal flow of control, it's basically linear down that whole block.
Yes, okay.
The compiler is not doing flow analysis and register calculation, et cetera, because of the presence of try-catch, even in a scenario like that?
The flow analysis pretty much fails when you cross between levels of try blocks. Okay, so if you have a variable that is entirely within a try block, it gets optimized and the data flow analysis works. But the data flow analysis between try blocks is what doesn't work very well. And optimizers usually, well, I can't speak for all optimizers, but from what I know, they usually abandon trying to track that kind of stuff.
Thank you.
So another way to think about it is if you could take your try body and put it in another function, that function would get optimized.
Okay.
And so that's how the compiler works.
On the memory side, it looks like in order to prepare for the heap being full, enabling exceptions makes it so that there's an emergency buffer that's created by default. Or, I mean, I think you have some control over it, but basically there's a buffer that's allocated for an exception in the case of the heap being full, so that it can still be caught. So you pay that penalty for the buffer, whether or not you have exceptions, if you have exceptions turned on. That's why there's there's a compiler flag for no exceptions. That's one of the reasons.
There's a little bit of extra overhead in C++ overall, just having exceptions in there. Runtime type information is included, because when the exception comes back, it has to figure out what type of exception was being thrown so it can get it and cast it and return the exception object to the catch block as of the appropriate type of object.
Well, the runtime type information, yes, is included, but it's not so bad because it's put in a separate page in your executable, and if you never throw exceptions, it is never even paged into memory. So it's not costly. Your executable size is bigger, but it doesn't actually consume any memory if you don't throw any exceptions.
Well, except for runtime type information is normally implemented through some offset pointers in the vtable.
That's correct. There's usually a pointer, an extra pointer.
And
when
which
you're
then, it's just extra garbage to drag around. And I've come from an embedded world, and I hate extra baggage.
Okay,
Yeah.
you're right. There will be a pointer to it, but the
Yeah.
actual tables tend to not get loaded in. For example, you cannot implement C++ on a DOS 640K machine simply because the RTTI is so large that you couldn't even get Hello World to fit in 640K.
Any more questions?
Would there be lots of overhead code if you had object creation, destruction, that now has to worry about try-catch?
Yep.
In the stack unwinding, there's space set aside for an alternate exit from the function. And it has to see, has this variable been created yet? Was it? Then call a destructor on it.
Wow, yeah.
Yeah. So I mean, so there's a fair amount of extra code, but if you don't call the exception, you're not running that code.
You're not running the code, but
It's there.
But is there, again, and kind of getting back to his point, is there extra code that has to get run even if you don't have an exception because of that for an object creation?
Usually, yeah.
Yeah, I mean, a couple instructions I'm not going to hassle to some extent,
Yeah.
but if it gets noticeable,
It's definitely there, and that's why most C++ compilers have a switch that says no exceptions and no RTTI. It's for that reason.
Part of the doing a no except on a function is just so the compiler can know that it's not really going to have to worry about an exception coming out of there. It's more of a promise that you promise to play nice.
Except that it's not really a promise to play nice, it's a promise to roll over and die if something, if there is an exception.
Well, that's the whole point.
If someone,
The gaming community, they keep creating their GIFs, their avatars, and then eventually they get to the point where they run out of space and the game just ends. So
if someone does, if some library you're calling throws an exception and you don't catch it, the default implementation is abort.
Yeah.
Yeah.
but I mean, but in the case of the games, people just say, "Oh, the game ended," so they don't really, been out of shape that it ended. But there are certain situations, especially like I know in C#, you're constantly creating web applications, and if the problem with the web that's not even in your application, yes, there's those kinds of exceptions that will be caught by external sources.
Something also needs to be kind of considered when we're talking about C++ versus other languages. Java is built to use exceptions. They're an alternate routine, an alternate exit routine, the way of returning errors, and you're expected to use them heavily.
When back when I was working here, they said, don't use exceptions for control flow. And oh my goodness, we use control flow exceptions all the time. It's considered part of normal programming practice in C#, really.
But again, it does affect performance.
You think we cared? You think we cared?
No, because C# is not very
Well,
good.
crash and burn isn't very good performance either. So.
No.
Well, and our thing was, and this is true of a lot of web services, I think, uptime and reliability, you don't get to bring the whole service down just because one potential thread died when you've got 100 more going, right? And that was something we dealt with quite a bit, was that concept. And so exception handling was all over the place for that reason alone.
And the direction that this discussion has been going is focusing on performance as if you were going into a try block in a low-level loop.
Yep.
Where you're going to do it a gazillion times and spend a lot of time there. Well, don't do that.
Right.
Well, yeah, so if you are going to be doing a try-catch around something you're doing a bazillion times, do it around the outside of the for loop, not inside the for loop.
Exactly.
Yeah.
The try-catch, you put the for loop inside,
Because one or two extra
put it in a
instructions
different...
that inside a for loop will cost you, a bazillion times.
Yeah, well,
later.
any function call inside, it's
Right.
like a function call inside a call loop. If it's not inline, it's going to cost you.
Right. That is something I'm going to bring up in the next.
Yeah.
A lot of calls are actually a lot cheaper than people think they are. Even if it's not inline, they're not
Yeah.
that bad.
Right. Yeah. It's. I don't want to overstate that, but we've been focusing on the performance cost and not on the system design benefits of using exceptions.
A myth about C++ is a lot of people absolutely refuse to use it because they say polymorphism is expensive. You have to do an indirect lookup.
Yeah.
And no, it's a lot faster than any other alternative.
Right.
If you do a switch statement or an else if, those are really expensive. You're doing a lot of stuff to look it up. Even the alternative of doing a pointer to a function, you have to spend time setting that up, even if you're going to be using it over and over again. And then the actual mechanics of doing the call through a pointer to function is a lot more expensive than a virtual call using vtable.
Well, in all those scenarios, you just took away the optimizer, basically. You're saying, I know what I'm doing.
Mm-hmm.
So you use a switch instead.
What's the optimizer going to do with a pointer? Nothing.
Yeah.
Yeah.
Right?
Right.
What is it going to do with it? No, but if a function call, it can go, oh, I can shift things on the register, or throw things off onto the heap. It can the compiler can sit there and do whatever it needs to do to make that thing work. You know, in a function pointer, you're just taking and saying, no, I know better than you, really, really.
Another little tidbit I'll throw out, just kind of my personal opinion. A lot of people try and do tricky code because they think it's super efficient. If you make the code readable and simple,
Yep.
it will be simpler for the compiler to read, and it will be able to compile it a lot better than you doing tricky code. Because your algorithm is just going to get in the way
Well,
of
that's
the
because the
optimizer.
compiler doesn't know exactly what you're interpreting, what you want.
Right.
So therefore, you may write some kind of specialized code, but the compiler will try to make it as simple as possible.
Well, you'd also be surprised at the tricks the compiler optimizers use.
Oh, yeah, they do yeah.
Go ahead.
Like try dividing by a constant and look at the code generated by
yeah.
a good optimizer. It's pretty shocking, actually.
I was just going to comment, even generally in GCC recognizes an attempt to do a circular shift by 7 bits. There's a standard code pattern, and it recognizes it, and it produces machine code that does a circular shift by 7 bits. So for some bits of code, the optimizer, it's been around long enough that the compiler goes, oh, I know what that is. So I'm just responding to saying if you write the code in too complicated a way, I would have thought shift by 7 bits, it's going to crank out who knows what. It recognizes it, so it's not hopeless.
So you're saying that that there's a sequence I could code that it would do a rotate instruction rather than shifts and ors and whatnot?
Yes.
Yes.
I'd love to know exactly what that sequence is, because there are so many times when I needed it.
Well, it depends on the compiler you use, but
True.
that's a normal optimization these days.
Another normal optimization along those things that the compiler recognizes, if you have an array you're trying to initialize, and you go through a for loop and call each element in that array and initialize it, it will figure out how to make that one really big mem set. So it can actually do it in one repeat instruction.
Yeah.
Any more? Well, thank you guys for coming, and
Even like
your
for some,
month.
you will define the structure
Next month,
or
we may
native,
have Sean
just
here.
native types.
Yeah, it's plain old data.
I invited him, but
That's more, and normally if you're initializing, you do all zeros.
he's
It's otherwise
he's a-
some complex data.
If it's